Okay, let's continue this with the concept of looking at other problems. Let's say we had a bolt, for example, although this bolt has no threads, and from a side view, from this person looking at it, what they see is a circle. However, what we can do is say, put this bolt through a piece of material that would be a certain thickness. Now, this material I'm talking about is a metal plate, for example. So what we have here is, from this perspective, this person sees a plate. So this is a metal plate, for say. There is a gap between it, and the gap I will not color. And the bolt itself is green. So what we're going to do is shove this bolt through here. This is a length L. But before we shove it through there, the gap on this, basically the gap being the distance between here and here, we'll say it's 0.01 feet. Fairly small gap here. Here's your gap. We're also going to fill the gap with a material. That material would be some sort of fluid. So basically you're coating the whole shaft in this fluid, and you're going to shove it through there with the force. Say the force ends up being 2 pounds. When we shove it, it's going to go at a certain speed. So let's say it goes in 0.01 feet per second. So it doesn't go very fast, so it's an oozy material that you basically put all over this. And it's all over here and all over, basically it's out here everywhere. So you're shoving this shaft through here. Say the length was 0.1 feet. We need to know the radius of this internal bolt, so to speak. So the radius we'll say is 0.1 feet as well. We already have 0.1, so let's make it 0.2. And the question is, what's the viscosity? Well, the first thing is you should take a look at this. Second thing is to address this. Is it a linear profile? In the cases in Chapter 1, usually it will be, with one exception, and that one exception we'll get to in a minute, and the next problem, or the next two problems, say. But for the most part, unless specifically stated otherwise, we're going to assume that it is. So if we zoom in on this region right here, what we see is the internal object, sorry, that's not a straight line. We see the internal object, the bolt, so to speak, moving along at a speed, and we see the outside of the cylinder, or the outside of the hole through the plate, being fixed. So we see a velocity distribution that looks somewhat like this. This time, y goes this way, away from the fixed location, out towards the bolt, so to speak. But you could continue to draw the bolt, and then you could draw the fixed object on the other side, in which case your diagram would look like this, and your y would go this way. So, as it turns out, we need to address all of these issues here. Let's address this issue first. What is the shearing stress? It's the force per unit area. And since it's a linear profile, I have the velocity over the gap. Move on down and let's start addressing. What is the force on here? Well, somebody told me the force. It's 2 pounds. 2 pounds. What's the area? The area is the wetted perimeter. Now, if you look at this from a side view, what you're seeing is something like this, an object being shoved through here like this, and this object may go on a little further, so it's basically being shoved through here. If I again made the red the fluid, you'd have fluid all around here, through here, and all the way out in here. Likewise over here as well. But the profile is only existing in one region. Let me see if I can draw that. And that one region is right here. In this region is where that profile exists. Out here and out in here, that profile doesn't necessarily exist, and there's nothing to produce a resistant force back in here anyway. The fluid's just being pulled into there. So the area is the wetted area that exists all along in here. It would be 2 pi the radius, which my radius, I'll just say radius, times the length. So I'll continue to do this way and carry it as a symbolic for one more. Now I can basically put in the information. I have 2 pounds there, 2 pounds over 2 pi. Now what is R? R was 0.2 feet. 0.2 feet. What was length? Length was 0.1 feet. Don't know viscosity. That's what we're supposed to find if I'm not mistaken. Yeah. And then the velocity. The velocity was 0.01 feet per second squared. 0.01 feet per second squared. And the gap was, I didn't specify the gap. Yes, I did. Here's the gap. 0.01 feet. 0.01 feet. Now, first of all, is the R very large compared to the gap? No, but in this particular case, it's different from the last case because the shearing is occurring in that way and not in this direction. In other words, if you looked at this, the shearing is occurring along the y-axis. If you look at polar coordinates look like this. You'll have a theta, an r, and say, let me replace that with a z. Since the motion is occurring in the z coordinate, you could represent it as polar coordinates or not. It would not matter. So if you want to now, you can basically move everything over. 0.01 feet times 2 pounds divided by 2 pi 0.2 feet, 0.1 feet, and then move this underneath. 0.01 feet per second squared, and you can carry out this calculation and get a number. So we can move on to another problem. Let's move on to another type of problem here. Let's say we end up with a situation in which water is being pulled down a hill. You've seen this all the time. So little river, so to speak, coming down the street, whatever. As it turns out, this profile is not exactly linear. And why is that? Okay, first of all, it looks a little bit like this. Here's why. If you look at a particular particle here, yes, there is a force on top of it, having it move in that direction, but there's also a gravitational force, something that has a component this way and one that has that way. This component doesn't do anything, but this component is pulling it in the direction that the motion is already occurring on. So this will create a different type of profile. We'll get into this later, but this could have an interesting profile. Let me give you an equation here. Let's say the if we consider this to be in the y direction and this to be the velocity, say little v, then little v will be a function of x. Generally it'll be, and I'm just going to make up some numbers, I would say 10 times say 0.01 y minus 0.001. Let's change this number to just 0.1. And that would give us y squared here. Now, in fact, I believe this needs to be 0.02. Now, if you had this equation, the first mistake I've made is this: velocity is a function of y. Then the question is, what would the shear stress be? Shear stress would be some constant. Say, let's just make the number of, say, 0.1. We haven't put units here, so we're not going to worry about that for the moment. And we're going to take the derivative here. 10 times 0.2y minus 0.01y squared. And take the derivative with respect to y. So if we go down here and take a look at this, what we have in essence is someone gave us a distribution, essentially an equation which relates the velocity in the layers. That's the key here. Really, all you've got to do is take a derivative. Now, I'm going to go through and multiply out some of this. So it would be 2. Derivative of dy is just 1. Now I'm going to have to make sure I carry the 10 in here and hit up on this. And I end up with 0.1 times the derivative of that is 2 times y and I get stuck with that. However, I can just go in here and put these two together to give me this. Now the first thing I could say is this: if I had, what is the shear stress when y was equal to 0? That'd be just putting in y is equal to 0, and I'd get 2 times 0.1, or that. What would happen if the shear stress when y was equal to, say, 10? If this were 10, then that would be 10 times that, and then this number with 10 here would give you that. Well, it just so happens this problem was kind of rigged. I took a few seconds to rig it, and that is that if this gap were, say, 10, then essentially this is the equation you'd get. You'd get the shear stress on the surface would be 0. Shear stress down in here would be 0.2 at whatever units I had here. I didn't use any units here. The whole key is this: someone gave you this, someone gave you that, and asked you the question, what is the shear stress at one layer? What's the shear stress at another layer? You can treat this as though, say, I took a sliver here. Yep. I took that sliver out, and that sliver is at a particular y layer. As a result, I'm going to have a shear stress distribution on it. If I make this such that it's very small, then these will pretty much equal outside of the fact that there may be an acceleration occurring, but if it's just flowing down here, there's no acceleration of this laminar So it gives you the shear stress at that particular layer. It turns out that in this particular case, you can see that the shear stress starts at a particular value in close, and this particular value is like 0.2, and then it drops down to 0 out here. So if you looked at the value, you'd go up, and it's linear. You can see it's linear. Starts at 0.2 near the wall, gets smaller until it's at 0 at the outside of at the top of the layer here. And I guess we could cover one other final type of problem, and it's nothing more than problems that you've seen before. Let's say you had a big block of, say, something slid down an incline, but underneath here it was sliding on a layer of, say, oil. The thickness of this gap, this is all oil here. So if you want to make it oily looking, let's make it green. So here's some oily looking stuff. The gap, or the thickness, might be 0.01, say, feet. If you were standing out here and looking down, this person would see something that was, say, square, and say the area of that square would be, say, 2 feet squared. Then say this angle was at 45 degrees. I like 45 because it's, there's 1 over square root of 2's involved. If you did a free body diagram of this and pulled this over to the side here, you would see something that looked like this. Let's say this thing weighed 10 pounds. Then this portion of it, 10 divided by square root of 2 pounds, isn't doing anything. It's just pushing against the oil. This part, though, is pulling 10 over square root of 2. Again, it's square root of 2 because it's 45 degrees. If this was 30 degrees, it'd be sines and cosines here. This part is pulling it forward. Therefore, that's the force. The area, here you go, 10 over square root of 2 is the force pulling this thing down this incline. The area is 2 feet squared, so this would be pounds, is equal to mu times, say this thing's sliding down here with the velocity equal to 5 feet per second. Moving a little fast, maybe that's a little too fast, but that's okay. Then the gap. Okay, now you have to remember this is from before. We're assuming a linear distribution. Now it is true that there are there is forces on the particles inside this layer, just like the previous problem. However, now I'm putting something on top of this and pulling it quickly. So if you pull it quickly, yeah, there still is a parabolic profile, but it becomes very, very minimal compared to the linear nature of the flow distribution, and you can assume it to be a linear distribution. And you can put in your 0.01. Now you can come back and figure out viscosity and just rearrange this equation. This is nothing more than tau is equal to mu dv dy. Now, I've gone through all these and I've found this. I've said, well, what is the viscosity here? What's the viscosity there? You can go through this and reverse these problems in all sorts of ways. There's no particular reason you can't say I have a viscosity of, give a number and say my force is this. What's the terminal velocity? Namely, what is this? So in other words, you're saying to yourself, okay, something has to be unknown. In the one I just talked about, that was unknown. Well, what happens if the force is unknown? Or what happens if the velocity is unknown? Generally speaking, the area and the gap are going to be fixed. So you have to be prepared for problems in which other things are unknown except the viscosity.